Hi, I'm Kathy. In this lesson, we're going to look at the graphs of some rational functions. Our specific objectives are the reciprocal function and the rational function defined by f of x equal 1 over x squared. But let's start with the general definition of a rational function. A function f of the form p over q, defined by f of x equal p of x over q of x, where p of x and q of x are polynomials, with q of x not equal to 0, is called a rational function. And you can see in the word rational, the word ratio. A rational function is a ratio of polynomial functions. Here's some examples. Functions like f of x equal 1 over x and f of x equal x plus 1 over 2x squared plus 5x minus 3 are ratios of polynomials and therefore rational functions. Let's start by analyzing this rational function, the function 1 over x, also called the reciprocal function. Well, notice that the denominator of the function is x. We cannot divide by 0. So as far as the domain is all real numbers except 0. We write that in interval notation from negative infinity to 0, not including 0, union the interval 0 to positive infinity. And now to continue our analysis, I want to approach 0, see what happens as x gets close to 0 from the negative side and then from the positive side. So I'm going to fill out this table of values. Taking the first value and substituting it for x, I consider what is 1 over negative 0.1, and that value is negative 10. 1 over negative 0.01 is negative 100. 1 over negative 0.001 is negative 1,000. As x gets close to 0 from the negative side, we see that the function gets close to a very small negative number. Well, let's see what happens as we approach 0 from the positive side. Let's put 0.1 into the function. Find 1 over 0.1. That number is 10. 1 over 0.01 is 100. 1 over 0.001 is 1,000. And as x gets close to 0 from the positive side, we see that the function gets very large. We can summarize this by saying as the absolute value of the function, or I should reiterate or say that again, the absolute value of the function approaches infinity as x approaches 0. And what I mean by the absolute value is f of x approaches negative infinity as x approaches 0 from the negative, and positive infinity as x approaches 0 from the positive. Well, let's keep that in mind and look at what happens as x gets very large or very small. So I've chosen some values of x that get large and a couple values of x that get small. Again, I'm going to put each value of x into the function. First, I'll find 1 over 100, which is 0.01. 1 over 1,000 is 0.001. 1 over 10,000 is 0.00001. Let me fix that. That's too many zeros. 0.001 and 0.0001. And what I can say is that x gets large, the function gets very small. We say the function approaches 0. Well, let's see what happens as x gets very small. First, putting in negative 100 for x, I get negative 0.01, then negative 1,000, negative 0.001. As x gets very small, we say that the function gets very small. Summarizing that particular information, we can say, again, x gets very large, the function approaches 0. X gets very small, the function approaches 0. We say there is a horizontal asymptote at the line y equals 0, the horizontal line y equals 0. And if you look back at our previous information, we say there is a vertical asymptote at the vertical line x equals 0. Now we should look at a graph and see what these two asymptotes mean graphically. A graph of the function And you can graph it on your calculator by hand. Looks something like this. And this is the graph of the function f of x equals 1 over x. What we saw in our tables of values was that x approached 0 from the negative side, the function got very small. As x approaches 0 from the positive side, the function gets large. As x itself gets large, the function approaches 0. And as x itself gets small, the function approaches 0. So our graph fits what we saw. We can summarize some other information about this graph. We can say that the function decreases. Notice that it's decreasing from negative infinity to 0, and it's decreasing from 0 to positive infinity. The function is discontinuous. Discontinuous at the point x equals 0. We can say that the y-axis is a vertical asymptote, is a vertical asymptote. We can say that the x-axis is a horizontal asymptote for the function. We can see also that this is an odd function. By looking at the graph, it has origin symmetry. And as indicated before, the domain of the function is from negative infinity to 0, from 0 to positive infinity. And looking at that, you can see that the range of the function is also negative infinity to 0 union 0 to positive infinity. So we get a lot of information about that reciprocal function. Let's look at an example that uses it. Here's what we want to do. We want to explain how the graph of f can be obtained from the graph of the reciprocal function y equal 1 over x. And we want to draw a sketch of the graph of f by hand and give the domain and range. And the graph f that we want to talk about is the function 1 over x plus 2. Well, first let's determine how this is obtained from this function. The graph f is a shift of 2 units to the left of the function 1 over x. What that means is the vertical asymptote of this function 1 over x plus 2 is going to be the line x equal negative 2. The horizontal asymptote will be the same as the graph of this function, and we'll write down the domain and range after sketching a graph. Well, let's see. We're going to sketch the graph of the function 1 over x plus 2. It has a vertical asymptote that is the line x equal negative 2. Other than that, the graph looks like the graph of the reciprocal function that we drew a few minutes ago. So let's draw in the graph. And let's write down the function's domain and range. The domain of the function is going to be from negative infinity to negative 2, not including negative 2, union the interval negative 2 to positive infinity. The range of the function is going to be from negative infinity to 0, not including 0, union the interval 0 to positive infinity. And I should indicate that this vertical asymptote is the line x equal negative 2. Well, why don't you try one like this? I want you to pause the video and work the following problem, then restart when you're ready to check your work. Here's what I want you to do. Explain how the graph of f can be obtained from the graph of y equal 1 over x. Draw a sketch of the graph by hand and give the domain and range. And the function that I'd like you to work on is f of x equal 1 over x plus 1. Pause the video now. Well, let's see how you did. This function is obtained from 1 over x by shifting 1 over x up 1 unit. The vertical asymptote is still going to be x equals 0, the y-axis, but the horizontal asymptote is going to be the line y equal 1, since the graph is shifted up 1. Well, let's sketch a graph. We're sketching a graph of the function 1 over x plus 1. The horizontal asymptote is the line y equal 1. The graph is similar to the graph of 1 over x, and so roughly looks like that. Let's write down the domain of this function. The domain is from negative infinity to 0, union the interval 0 to positive infinity. The range is from negative infinity to 1, union 1 to infinity. We're ready to move on to another rational function. Let's look at the function 1 over x squared. This function has some similarities to the reciprocal function that we worked with. Since the denominator is x squared, we see that the domain is all real numbers excluding 0, so the interval negative infinity to 0, union 0 to positive infinity. And rather than taking time to fill out tables, I can see that the vertical asymptote for this particular function is going to be 0, in that as x approaches 0 from the negative side, the function's going to get very large, actually get very large and positive because x is squared. And as x approaches 0 from the positive side, the function is going to get very large and positive, since the function is 1 over x squared. As x gets large, goes to, say, positive infinity, the function's going to get very small. And as x gets very small, goes to negative infinity, the function's going to get small. And so a graph of the function looks something like this, only a little smoother than what I've drawn. And there's some other information that I want to write down. I've written down the domain of the function. Let's write down the range of this function. Notice that the function extends in the y direction from 0 to infinity, not including 0. And that's the range of that particular function. We see that the function increases on the interval negative infinity to 0, and that the function decreases on the interval 0 to positive infinity. We see that the function is discontinuous at x equals 0. As a matter of fact, that there is a vertical asymptote at x equals 0, that is, the y-axis is a vertical asymptote for the function. The horizontal asymptote is the x-axis, and I should indicate that. Horizontal asymptote is the x-axis. And finally, I want to write down that this is an even function, in that it has y-axis symmetry. Well, let's look at an example that uses this function. Here's what we want to do. We want to graph the function y equal 1 over x plus 2 squared minus 1. And we want to use the graph of 1 over x squared to get our graph. Notice that this is a shift of 2 units to the left of the graph of 1 over x squared, and also down 1 unit. What that means, as we draw our graph, is that the vertical asymptote is going to be at x equal negative 2. So there's our vertical asymptote. And the horizontal asymptote is going to be at y equal negative 1. And now, using these two as asymptotes, we draw a graph similar to the one we drew a few minutes ago, and we have the graph of y equal 1 over x plus 2 squared minus 1. Well, in this lesson, we've just looked at two kinds of rational functions. Be sure to work lots of exercises from your textbook for practice.